In this video, we're going to do another stoichiometry practice. So in this case, here is a reaction. Rust plus aluminum goes to aluminum oxide and iron. We have two questions we want to determine from this. If 15 grams of aluminum is going to be reacted, what mass of the Fe2O3 is also needed? And second question, if 15 grams of aluminum is reacted, how much iron product is produced? What weight of it? Give those both a try, and then come on back for the guided answer. All right, if you're back with us, well, first thing first, I have a reaction, but it is not balanced. You'll notice I have only one aluminum on the left and two on the right. I need to balance my reaction so that I can convert from one element or one compound to another compound. And so if I have two aluminum on the right, I'll need two on the left. If I have one aluminum oxide on the right, that gives me three oxygens. I need three oxygens on the right, which means I need only one Fe2O3. But that's going to give me two irons on the left, so I need two iron on the right. So it's a 1 to 2 to 1 to 2 reaction. First, let's say I've got 15.0 grams of aluminum. I want to find my grams of Fe2O3. Well, I cannot compare grams of one compound to grams of another. I have to be in moles. So really my first step is I need to find moles. And the only way to find moles is to find molecular mass. So I need to find the molecular mass for each of my compounds. Well, iron, 2 times 55.85. Oxygen, 3 times 16.00. 159.7 grams per mole. And so 159.70 grams per mole. Aluminum is just what it says on the periodic table. Each aluminum is 26.98 grams per mole. The fact that there are two in the balanced reaction doesn't change the formula. It's a single aluminum, and molecular mass is based on the formula. Molecular mass of iron, similarly, is just what the periodic table says for iron, 55.85 grams per mole. Aluminum oxide, on the other hand, we're going to have to add up 2 times 26.98 plus 3 times 16, 101.96 grams per mole. So we have our molecular masses that we're going to use to solve the rest of our problem. So back down here to our aluminum, I need to go from aluminum and I need to get it into moles of aluminum. So I have grams of aluminum, 15.0 grams of aluminum. I need out of grams and into moles of aluminum. 26.98 grams of aluminum in every 1 mole of aluminum. And so when we multiply that's and divide, 0.55597 mole of aluminum. Once I have my moles of aluminum, I can get out of mole aluminum and into mole of Fe2O3. My balanced reaction said it was 2 aluminum for every 1 rust. So that is 2 moles on bottom and 1 on top. So I'm going to end up dividing this in half. 0.27798 mole of Fe2O3. And in the end, we want our weight of Fe2O3. And so I need to convert those moles into mass. 0.27798 mole of Fe2O3 I need to get out of mole of Fe2O3 and into grams of Fe2O3. And so I need a molecular mass. To go from moles of a compound to grams, I need its molecular mass. We said 159.7. So 159.7 grams in every 1 mole. 44.39 grams of Fe2O3. And at the very beginning, we had 3 sig figs. Our molecular masses were 4. Balanced reactions are perfect. They don't affect our sig figs. So we're maintaining 3. Our iron oxide mass was big, so we get to keep 3 at the end. So this is really 44.4 grams of Fe2O3. For 15 grams of aluminum going in, you need 44.4 grams of the rust, of the Fe2O3. Second question, if 15 grams of aluminum goes in, what mass of iron is produced? And so second question, I have 15.0 grams of aluminum. Well, same starting. I can't compare two things in grams. I need to get out of grams of aluminum and into mole of aluminum. So 26.98 in 1 mole. As we saw up above, that was 0.5559. But the next step was I did the balanced reaction. Now I can write it out, or I can just multiply the next one. I can just get out of mole of my first chemical and into mole of my second chemical. So this is a little way to be a little faster. Since when I do my multiplication division of my first part, I'm just going to immediately multiply it and divide it again. There's no reason I have to write it each time. I can just chain these together. What is my mole of iron and mole of aluminum ratio? We'll back up at our balanced reaction. It was 2 and 2. And so there are 2 moles of aluminum for every 2 moles of iron. Now I could stop there. What I'd do is I'd go and I'd solve the moles of my iron, the same way we solved iron oxide last time. But immediately following, I just multiplied that value by my next conversion. And so I can do that again. I can just multiply this by the next conversion. I want out of mole of iron and into grams of iron. Well, our balanced reaction said for every 1 mole of iron, our molecular mass said for every 1 mole of iron, there is 55.85 grams of iron. And this will be 31.05 grams of iron. Again, we had 3 sig figs, and then 4, infinite, and 4, so we will keep 3 sig figs. This is 31.1 grams of iron. So for 15 grams of aluminum going in, I make basically a little more than twice the weight of iron. That's because iron, well, look at the weights, 26 versus 55. It weighs a little more than twice as much. So in this case, we can use aluminum to find both how much of the other starting material we require and how much product we will make. You'll notice that we didn't need to use the aluminum oxide molecular mass. We solved it. It was 101.96. But since none of our questions asked us to find out anything about aluminum oxide, it isn't actually necessary for this problem, or these two problems. And so sometimes you need to find all molecular masses. Sometimes you only need to find the ones that you have values for and are trying to find values for.